Jasper Kager here from Istituto Superior Tecnico. He's going to speak about exact solutions to matrix models and string theories. So please.
Thank you very much, and thank you to everyone for coming and for having me here, especially to Alessandro, of course. I'm going to take this opportunity to talk about my work that I did for my PhD in collaboration with the resurgence group in Lisbon, with my advisor Ricardo Schiappa, his former student Max Schwick, and his current students João and Noam, where we answer the question, how do we non-perturbatively complete perturbative string theories? So, as you know, a string theory tends to be initially defined via some genus expansion, which is both perturbative only and is an asymptotic series due to the factorial growth of the expansion coefficients. And so it's a fair question to ask, how do we figure out which non-perturbative effects should be added to this to get a full non-perturbative theory? And I will show in this talk that in the case of matrix models and their double scaling limits, we can actually find a complete description of the non-perturbative physics and combine things to a manifestly background independent full non-perturbative completion. And from a physical point of view, we will see that positive and negative tension instantons will both come into play. So let me first outline the talk. So I will explain what resurgence is, how it works, and how it can lead to non-perturbative insights into our theories. Then I will introduce the models that we've looked at and the solutions that we claim to have found. So resurgence is a way to, in a sense, make sense of asymptotic perturbative series where we start with some asymptotic genus expansion, if you will, or perturbative expansion in some coupling X, and we apply a Borel transform, which divides out the factorial growth that we're worried about, and that results in some series that has a finite radius of convergence in the Borel plane or S-plane. And so after some suitable analytic continuation, we can invert this first step by a Laplace transform. Turns out this is the inverse of that. And then the resulting object is a well-defined function now that you can plug numbers x into and it spits out finite numbers for you. And that has this original object as asymptotic expansion. Now, this procedure, as I outlined it, is ambiguous to some extent because this analytic continuation down here turns out to often have singularities. And so when I take, which I show here in green, and so if I take a Laplace transform of this, it matters whether I choose that integration contour or that one because of this green stuff in between. Now, how much these two differ depends on the exact singularity structure in between, but we will only look at problems where these singularities are logarithmic. And in that case, the Laplace transforms or your resummations on neighboring wedges turn out to differ by an expression of this form where we recognize immediately from a physical point of view the exponentially small corrections that we assign to non-perturbative physics and physical objects. And then F1 is going to be some extra perturbative expansion that we would then need to go through this entire loop to make sense of. Now, what this means is that our initially perturbative series now should be upgraded with these non-perturbative objects into a trend series where upon Borel resummation of all of these series expansions, the resulting object is a well-defined function in some Stokes wedge, as we call it, on the original coupling plane, which the boundaries of which, or Stokes lines of which, basically correspond to the locations of these singularities. And so if we want to analytically continue from one Stokes wedge into the other, what we have to do is to take into account all of these crossings of singularities, and that can be compactly packaged into what we call connection formulae, which are just introduced changes of these boundary parameters in our fan series. And so once we do that, and once we correctly resum everything, we are done though. We have a non-perturbative, we hope to have a non-perturbative completion of the theory that we care about. And I will show you in this talk that we can do this explicitly in the context of matrix models. So let me now introduce the main player of this talk, which will be the Hermitian matrix model partition function, which is some integral over large n-dimensional matrices, or equivalently over matrix eigenvalues lambda, and those two descriptions are equivalent, but they differ by some Jacobian determinant delta, which I will not be explicit about. Okay. Now, this object is interesting because on the one hand, it's just complicated enough to admit some interpretation in terms of gauge theory and string theory, but it's simple enough for its non-perturbative effects to be completely classifiable. And this is important when you want to do resurgence, we can do high genus and high instant on large n calculations in this setting. And that will allow us to make contact with the first part of this story. So let me start by unpacking this last part. So we can do this matrix integral very efficiently and cleanly by introducing what are called orthogonal polynomials. And this relation defines for you both what we mean by these. It defines what these polynomials are, what we mean by orthogonality of them, and it defines the Hermitian, the square norm of Pn, which we call H. Now, if you play around with this a little bit, you will see that these polynomials satisfy some simple linear recursion, where I want to bring your attention to this norm of Stokes ratios that's in here, because once you know all of these Rn's, you can perfectly, non-perturbatively, fully reconstruct the partition function from them. And so, if we want to say something intelligent about this partition function, we can try to do it indirectly by saying something intelligent about these Stokes ratios, about these norm ratios. And the trick that we will use here, which I will not completely explain how it works, is that these ratios define or satisfy some recursion of their own, which we call the string equation. I will not show you exactly how those things are derived, but just to give you a feeling for what this looks like, if we choose as a potential v in our matrix integral a quartic polynomial, the string equation that we find looks like this, where now it's very easy to construct all of these Rn's, which then gives you your partition function in full with very little work. And now the reason why we're happy about this when we want to do resurgence is that we can analyze this type of equation from a large n point of view. So we can take a large n limit, which involves upgrading this n gs to a continuous variable x and this little r to a continuous function r. And then we find some string equation that we can hope to analyze and understand as a non-perturbative, as defining some type of non-perturbative completion. Yeah. Yes. Originally, it's true for finite n, but this can be made sense of at the large n limit as well. The trick there is to pass through the free energy first. So you take a logarithm, and then the product becomes a sum, and then you can take a large n limit of that, where that sum becomes an integral. This is finite n, but there's an equivalent relation of large n that will make all of this work. Yeah. It's this original partition function matrix integral. Well, the potential, the v, we assume to be a polynomial, yes. Yeah. This is this is how we define an orthogonal polynomial. What we mean by, you can kind of think of this as an inner product between your polynomials. No, this definition is independent somehow. Well, this polynomial potential is in here too, but yeah, originally you can define this independently from your matrix integral. It's just that, like, there's this nice relation that makes things work. Yeah. Yeah, so I didn't make that explicit. Those are not as important for us, but the SNs are basically, you can write them in terms of these P's in a simple way as some integral, like it's the first moment of your P, basically. I didn't make that explicit here because that part is not as important, but yeah, these can be compute. Once you know Pn, you can compute S, you can compute R, and then you can compute your next guy, and then you repeat. Thank you. Yeah, this is a generalization of all of the standard ones, like Hermite and Kager, and yeah.
Okay, the dependence on the potential is basically in this.
It's in here, yeah.
No, if you when you write the recurrence relation, is in this Rn the dependence on the potential, basically.
Yes, yeah, right.
So the minus like multiplication by t gives a linear combination of three orthogonal polynomials, so you can have expectations with those scalar products.
Yeah, right.
Okay.
Yeah, and this is a generalization of like Hermite polynomials, for example. If you choose V to be a Gaussian potential, then you get Hermite polynomials out of this, and this is the recursion relation of that. Yeah. Thanks for the questions. Right. So now that we have our string equation and we took a large n limit, what we want to do is to analyze the solutions to this thing via train series. This was done almost 15 years ago now for this particular problem, where it turned out that the full non-perturbative train series that you will find has this form, where the sigmas are the boundary parameters I showed in the resurgence part, and these are the instanton actions that control your non-perturbative effects. And then these numbers are n and g, and now we constructed the very high n's, m's, and g, and then we're happy because then we can play resurgence games. And then if you compute a couple of these coefficients explicitly, you will see that, and you look at them for a bit, you will see that those coefficients have singularities at some finite value of the adult coupling. And for reasons I don't have time to go into, this is a point where string theories emerge. So what you can do is you can take what's called a double scaling limit, which involves approaching this critical value in some controlled way and well-defined way while taking n to infinity in a way that such that this limit is finite and gives you a non-trivial answer. In the case of the quartic matrix model, this gives you the Pavlov-1 equation, where now Z is like a linear rescaling of X around this critical value, and U is basically the part that survives this process, the part of R that survives this process and that controls the behavior around these singularities. Now, in this case, we find the Pavlov-1 equation, but this is just the simplest possible outcome in an infinite hierarchy of outcomes called the KDV hierarchy of multi-critical string theories. You can get the other elements by considering more complicated matrix potentials and then playing a similar game to this. Now, the more general string equations will always look like some differential polynomial in U, so polynomial in U and its derivatives equals Z. There's some explicit recursion for how to compute these for any k. This is quite simple, but I won't go into it. And what I will point out is that you can use these R's as building blocks to build string equations that give you more interesting string theories. So if you weigh them by appropriate KdV times Tk, you can obtain minimal strings, you can obtain JT gravity, you can obtain Argyros-Douglas theories. And so what this gives you is a very clean, explicit differential equation that you can analyze to get non-perturbative insights into the theories that you care about. And resurgence is one convenient way to do that. So you can now take your favorite element in this class and you can plug in some trans series ansatz and compute a whole lot of data and then take things to the Borel plane and see what non-perturbative effects you find. This is the outcome of that process for the Penrose-One equation, perturbative sector, where, so what we used here is a numerical procedure called Borel-Padé analysis. That's like a numerical approximate analytic continuation process, where the important part is that these black dots line up around logarithmic branch cuts on the Borel plane, and these blue and orange dots are the instant-on actions that we expect to find. And so we see two obvious singularities here, where a blue instant-on action, which is positive, so it has positive tension, and then an orange one on the negative line, which has negative tension. So all of this is very convenient computationally, but it's not so obvious what all of this means. It will be nice to have an alternative, more physical interpretation of this. And the way to do that, to get that, is to go back to our starting point. So we say, well, we're just doing some integral, right? Why don't we do steepest descent analysis on this integral? So you can do this. So you can, first question there to answer there is which eigenvalues lambda do I choose to extremize this integrand? And then we build GS corrections around that. And the lambdas that extremize the integrand satisfy this equation of motion, quote unquote. It's an algebraic equation. It's not differential, but this is what we call it. And now what you can do is you can just handpick some large value of n, some value of t, the coupling t, and you can just plug this into a computer and see what eigenvalue distributions you find. We did this explicitly for the cubic matrix model, where this potential v is a cubic polynomial. And it turns out that there are three topologically distinct solutions, options for this in the complex t-plane. This is the complex t-plane. At weak coupling, we find that things align on one line or one cut. Then at stronger coupling, there are two regions where things line up along two cuts. And then as you go to stronger coupling, these two merge and you find a trivalent tree configuration. Yeah. Yeah. That's right. Why the integral still makes sense, you mean? The matrix integral? That's a fair question. Yeah, so that has to do with the integration contours that we choose. These are not just from minus infinity to infinity, because indeed, if you do that, you will run into convergence problems and analytic continuation issues. The integration contours that we choose are Lefschetz symbols or steepest descent contours. I will get to that. I will make that explicit later. But thank you for that. So the point here is that the reason why I show all of this is that we can now think about these things from a large n point of view. So we can take this large n eigenvalue distribution that we find and upgrade it from the large n point of view to what is called a spectral curve. I will not go into the definitions here, but what's important here is that the spectral curve is some algebraic curve that for the problems that I care about has two sheets that I will show pictorially in blue and in orange, and those two sheets are connected by one or several cuts and one or several saddles. And we will see that, well, things are defined in such a way that the eigenvalues line up along the cuts. So the cuts here give you your perturbative physics, and then the saddles, I will show you momentarily, give rise to non-perturbative effects. Now, we can use this spectral curve as the basis for a perturbative iterative calculation to compute your genus expansion that I was talking about. This is done through topological recursion. I don't have time to explain how that works, but this is a very well-defined, very well-established technique that works for all of the models that I'm talking about here, has been proven to work. And most importantly, if you run topological recursion on these spectral curves, you match the stuff that we found through that perturbative string equation that I was talking about. But now what about non-perturbative objects, though? How do we match parts of our train series that we got from the string equation to parts of this matrix integral that I said was the starting point of this story? What parts of this matrix integral correspond to a given sector, for example? And to answer that question, it makes sense to think about this again from a resurgence point of view, where we can start from just the perturbative sector. So we just choose our sigmas to be 0 so that we only have a strictly perturbative object. And then we Borel resum things and we cross Stokes lines, which switches on non-perturbative objects. It then makes sense to try to answer this question of matching things by saying, what happens? How do matrix integrals see Stokes transitions? And the answer of that, what Stokes transitions look like, actually lie in the integration contours, and now I'm getting to your question. The integration contours are Lefschetz thimbles or steepest descent contours, which pass through the optima that I was talking to you about, and they shoot off in whichever direction essentially makes this integrand fall off the fastest. And then a Stokes transition turns out to be a discontinuous jump in the asymptotic directions of that contour. So for the cubic matrix model, the integration contours might shoot off in that direction and in that one, and then as you cross a Stokes transition, a Stokes line, suddenly the contour jumps from going into that direction to going up into that direction. And yeah.
Confused about the logic. So
yeah.
Let's say given a physical problem, then the contour is fixed. Let's say naively the one that we have ever seen in the everything else, let's say, but not necessarily. Say the physics will tell you what contour is, the one you want to study, let's say physics. Okay? Then you want to decompose it in Lefschetz symbol, so it's making sense.
Sure.
And this is how, from the point of view of the integral, so whenever an asymptotic series is coming from an integral, it is well known that the Stokes constant arises as intersection number of the Lefschetz intersection. So decomposing your C into sum of thimbles, and this is typically, I mean, this in simple example is one-to-one with the formula above. So, but it's not that I start by, I mean, you can also starting the integral from a given a Lefschetz symbol, but it's not really physical, right? So this comes out as a. So I'm not sure I understand the logic. So typically, what I have to say is that you have a problem of physics motivated,
sure,
which singles out a specific contour, which is typically the real axis. I mean, the variables are taking real values, right?
Yeah.
Then all your consideration requires that this might not be well defined, so you have to decompose this contour into Lefschetz symbol. Then you ended up studying the integral over the Lefschetz symbol.
Yes.
But then you have a sum of them because you are decomposing the whole Lefschetz symbol and the specific weights how you sum all the Lefschetz symbols component are given by intersection numbers of the Lefschetz. Okay. So is this the logic? Because and then I believe you will get the sum over element. That's the typical. So is that which logic are you using?
You can say that we're using this logic initially to define this integral on the real line, for example, for real values of your coupling. But then, as I pointed out before, since the potentials that we're looking at are polynomials, there's like a limited, like, you can't, yeah, there are polynomials, and then there's always some limited regions that you can actually shoot your integration contours into, that will lead to the integral making sense. So now if you then want to analytically continue things into the complex plane, you can only do so in a limited capacity because, like, while keeping your steepest descent contours fixed. That's a point. If you take, yeah, so let's hope that this works. Yeah. So for the, not great. Is this a chalkboard also? Does that work? Not really. Okay, well, okay. I can try to describe things in words. Essentially, if you are insistent on keeping your integration contours fixed and not move them, there's always only a limited convergence region to this integral. If you make the argument of your GS too large, then things stop working. And so it makes sense to then just say, okay, then I will make my integration contours, I will allow my integration contours to move.
I mean, this is standard, right?
Mm-hmm.
Now, what is the logic? What is fixed? Let's say, what I want to land on is this, let's say, fixed C, because this is physics. I don't know, this is the string partition function whatsoever. This is a specific contour. Then to do my resurgence analysis, blah, 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 I need to study this in different contour. But then what I just wanted to emphasize is whether you are looking at this Kager-Lefschetz intersection numbers or not, which will fix for you how to decompose your original contour, whatever it was, but it was a fixed contour, into the one that then you want to study, which are well-defined, which are Lefschetz. This is the point I'm making.
Oh, I see. Right. Yeah. Yeah, that's okay, yeah, that, I realize that that's the question now. Yeah. No, we are a bit more flexible. We allow the weights of your Lefschetz symbols to vary more. So we basically choose them to be arbitrary, and that gives rise to your sigma 1 and sigma 2. Those give you the weights that you assign to your contours. And for our purposes, it makes sense to actually do this because, well, as I told you, if you do this decomposition and then you analytically continue enough, eventually you will have to cross some Stokes lines, and that will force you to change your contours. Right.
Okay, let me tell you why I switched. Joao already came here giving your collaborator. So we were already, some of us were already exposed. And then the question that I was sort of starting anticipating when we do it, this report, is that if you start with a physics-wise question, I wonder whether this negative tension breaks enter at all. But maybe we can.
Yeah, let's discuss about that later. Okay. Yeah. Okay. So essentially, the story that I was landing on now was that these Stokes transitions allow you to like change the asymptotic directions of your integral, of your contour, and the difference between these will always be some steepest descent contour that passes through the non-perturbative saddle. And so what we say, we like to think of this as an eigenvalue having tunneled from the perturbative cut to the non-perturbative saddle. And so if you make this eigenvalue tunneling picture mathematically precise, you will see that you can actually, from this integral point of view, reconstruct part of your trans series. The part where positive tension stuff is switched on and negative tension initially is not. And then this was done in 2008, 2009. And then a natural question is, how do you also see negative tension effects in this picture? And it took some 15 years for it to be realized that the way to do this is to tunnel things, to tunnel your eigenvalue, not through this sheet, but to the other one. And there's a way in which your eigenvalue sees which of these two sheets it's tunneled through. I won't go into exactly how that works, but this is true. And if you make this precise, you will match negative tension effects that you see also from the string equation point of view. Now, you can now naturally tunnel things through both sheets at once, and you can get fully generalized mixed sectors from the eigenvalue tunneling point of view now, which now fully gives you an alternative way to build your trans series, but now from a more intuitive perspective. So we've seen two ways of doing things, orthogonal polynomials and spectral geometry, and orthogonal polynomials is a bit more abstract, but is a computationally very efficient technique that lets you do resurgence, and then spectral geometry and eigenvalue tunneling gives you an alternative way to look at things. But so now, what we wanted to do for our problem, for our project, was can we combine the best of both worlds here and obtain exact solutions to these problems from the large n point of view? And I will show you that we can. So the final piece of the puzzle for us was to look at this trans series for the free energy or the partition function or for R or whatever you want, and realize that there's a lot of values of n and m, a lot of different sectors that have the same exponential weight. And so it makes sense to try to group like powers of exponentials and see if you can somehow resum things of like exponential dependence. And this turned out to be possible, and the final result and the form for all of the objects that we've talked about turn out to take the form of a Zach transform or a DFT, if you will, where I will go into exactly what all of these symbols mean, but basically there's one function, Z2 cut, that you can take a DFT, a discrete Fourier transform of, and weigh things appropriately to get the full non-perturbative answer out. This is the answer for the cubic matrix model and for Pellevey, but there's more complicated generalizations of this for all of the other models in our class. Where now mu is like a product of these exponential weights, and then mu1 and rho is basically the positive tension weight. Now, this Z2 cut that we'll get into in a bit is still an asymptotic series, and so you need to play a resurgence, genus, expansion, resummation game, which means you will still need to cross Stokes lines and and then you need connection formulae to fully define things for all couplings. And we say, and we've seen that the connection formulae that you need are equivalent to those given by some that also appear in some topological string settings, as pointed out by Iwaki and Mariño. Yeah. Yes, I'm getting into that now. Thank you. So Z2 cut is a two-cut topological recursion partition function, where now we run this topological recursion process on a spectral curve with two cuts. And here the parameters T1 and T2 are filling fractions, so they define for you, they tell you how many eigenvalues you put in each of your two cuts. And so you can run your topological recursion and get a sector from your trans series. And basically what we're saying now is that you can get the full non-perturbative picture from this, the other being the other sectors on the previous slide, just by moving eigenvalues back and forth between your cuts.
What is the meaning of that infinite sum, where the number of eigenvalues is always finite, so the sum should always be...
Yes, so that's a bit of a subtlety in how finite and large n match. But what I said is an intuitive picture, but this is how you can think about it as a sum over large n backgrounds, but sure. And so essentially this process of tunneling eigenvalues back and forth gives you the full answer, the full non-perturbative answer. And if you put in a bit more work, you can actually prove that this thing is fully background independent, in the sense that you have some freedom to choose what T1 and T2 you choose, because that's what gives you, because like I said, T1 and T2 is a choice that you put in. And so now we have to be careful though, because this picture seems quite different from the one that I showed you in the first half hour. And so we better make sure that things match what I said before. And so since we can choose what T1 and T2 are, we can choose to go back to the former setting that was built on this spectral curve, essentially by just letting T2 go to 0. And doing this, we do see a match between what I showed you, the 2-cut answer versus the 1-cut answer. And as an added bonus, letting T2 go to 0 actually requires a Gaussian regularization to be well defined, and that reorganizes your trans series into this more gauge theory like form, where now we can compute these decay polynomials explicitly in terms of spectral geometry objects. These can be computed directly from first principles now. And now, of course, what I've shown you here, I've only shown you stuff here about the cubic and like simple spectral curves, but we can easily generalize this to more complicated settings. So, for example, the 2,5 minimal string is described by this spectral curve that now has one extra saddle. And now you can do this sum over eigenvalue distributions game and get the exact answer also there. And then doing this pinching game, you find this very similar structure where, again, we can get these polynomials in mu1 and mu2 explicitly from spectral geometry calculations. We've tested this for a lot of different models, and it always works.
Sorry, a question, but the previous solution you showed, that one is basically a solution of the one of the equation.
Yes, on double scaling, yes.
And instead, this one, do you know which kind of equation satisfies? No, also because
yes.
Like the KDV hierarchy.
Yes, this is the second element of the KDV hierarchy, for example. Yes, you can explicitly construct this in terms of those. Yeah. Yes, exactly.
The L run over all possible integers.
Yes.
So what is here what you would call it perturbative answer, the perturbative part of this subject?
Yeah, so if you reorganize things in this way, in this pinched way, I would say L1 and L2 equal 0, because that's what gives you a match to what we called perturbative matrix integral. Yeah.
The negative L are exponentially enhanced.
Mm-hmm. Yes, that's what gives rise to your negative tension objects. Yeah. Mm-hmm. Mm-hmm. Sure.
Is it possible to make this exponential oscillator or not?
Say again?
Is it possible to make this exponential oscillation in some region?
Yes, but using some alternative resummation techniques, we can actually make sense of this also when in regions where the exponentials are not oscillatory. or strictly oscillatory. But we'll get to that. Let me skip some of this. So now, all of this gives us several different large N ways of viewing these models, but I started this talk by saying that the Hermitian matrix model partition function, which is our main player, is some finite n-dimensional integral. So we can now still ask, can we take this large n points of view and go back to the finite n point of view and show that we can make concrete predictions also in this original setting using all of the tools that we've developed, and I will show you that we can. So we can use our partition function to compute orthogonal polynomial norms using this simple relation. I won't show exactly how that's proven, but this is not too complicated to do. And now you can compute these numbers along some ray on the complex D-plane, and you can ask, can the large N objects that we've constructed reproduce all of this complicated behavior? So we can add the phase diagram, phase shading, the one-cut gray region, the two-cut blue region or green region, and the trivalent red region. And we can ask, does the large N trend series reproduce all of this? And the answer is yes. So the red line here is the large N resummed large N predictions, and the blue line is the Stokes line. And we see that that all of this actually works for all couplings in all phases that we've seen. And this is one particular cubic matrix model, but we've tested this for a bunch of other models too, and it always works. So I should point out, though, that this only works if we add negative tension effects. So in this picture, the black line is actually finite N values now. Sorry for the change of style there. And the blue dots are large N predictions. And we see that things work, that things match very well right up to the Stokes line, at which point the finite N data stays continuous, while if you ignore the Stokes transition, the large N predictions discontinuously jump, unless while the Stokes connection formulae that we showed fully fix the match. And now the thing is that this Stokes transition is exactly what mathematically switches on negative tension effects. And so if you don't add negative tension stuff, this will not work into arbitrary strong couplings. Eventually things will fail. So and there's a different way to see this, like even if you were in a regime where this jump is not as dramatic, you can go to arbitrary strong couplings. You can go to strong couplings and also see that positive tension alone is not enough. But then you can still say, well, maybe you just picked N large enough that things appear to work. So what we did here is we fixed values of the 12th coupling in each of the phases that I've shown you, and we varied N. And even then we obtain full matches between the finite N circles and the large N blue and orange lines, which tells you that this story actually works for any N as large as 100 and as small as 2. Even though, I should point out, in the two-cut and trivalent phase, you can actually see a lot of oscillatory non-trivial behavior on many different scales that is fully captured by our large N objects. And now you can still say, hold on, the large N matrix integral or the finite N matrix integral was a simple finite dimensional integral that was surely single-sheeted in T, while the large N trend series, like the trend series data that you've shown, appears to be multi-branched. So how do you reconcile these two things? And to make this more concrete, if you would look at the cubic string equation, a leading order, you will find this relation, which clearly has three different solutions. So you can imagine building a trans series on top of using each of these three. So if I tell you finite n matches large n, one, I better tell you whether the large n solution I'm talking about is the one that lives on this gray sheet, or this lighter gray sheet, or this translucent sheet. And I better tell you that all of these things, once you add in all of the non-perturbative effects, all of the genus corrections, all instantons that we've been talking about, and you correctly implement all of the Stokes transitions, all of the Stokes lines shown in blue and in orange, all of these trans series match the same finite n objects. This better happen, and it does happen. So in this plot, the black line is finite n data again, and the gray and the orange are large n trans series that live on two of these three sheets, and things decisively match in the green region. We lose precision here. Gray loses precision here because of lack of data. Orange loses precision here because of lack of data, but we still think that this is a very convincing argument that things are actually consistent also in this sense. And now we can do even crazier checks, and we can compare roots of the partition function from the finite n and large n point of view. So in this plot, the gray and the orange are roots of the large n partition functions, and the boxes show you regions where the finite n partition function has at least one root, which we obtain through some numerical techniques I will not go into here. So if we want to say that finite n matches large n, the dots better fall in the boxes, and they do very well everywhere in the upper half plane, and they're either do or are very close in the lower half plane. We lose precision a bit here. That's again because of lack of data, but this is still very convincing, I think. And now we can do a similar check to double-scaled models. So this is the next element in the KDV hierarchy. This is a double-scale theory now. We can do an analogous check here. So in here, the red dots are the double-scaled versions of these gray dots in the orange. So they're the roots of the large n partition function, and then the black lines are level curves of a numerical solution of this equation. And we expect the red dots to fall in the points where the black lines accumulate. And so we can correctly account for all of the different roots everywhere in the coupling plane, despite the fact that this is a very non-trivial fourth order differential equation. So my trans series is now four-dimensional. There's 4 boundary parameters, and there's 6 different Stokes lines shown in blue and orange. So each comes with slightly different connection formulae and Stokes transitions. So the fact that all of this matches everywhere is a highly non-trivial check that everything is consistent. So let me wrap up this. I've shown you an exact large n solution to matrix model partition functions that we believe is completely non-perturbatively complete. And we can use resurgence and resummation techniques to take this initially formal object and make sense of it in such a way that we can plug in numbers and get concrete numerical predictions for finite n objects. And now we are working on a couple of follow-ups to this project where we want to generalize what we did to correlation functions and, the matrix model version of observables. And we want to go to more complicated theories than our Hermitian matrix models with polynomial potentials and go to examples like JT gravity, super JT gravity, and ABJM theory. I'm still working on this one. These two are in the works by other people in my group, and we have early signs that things also work in those more complicated settings. Thank you very much. Yeah.
What was the origin of those oscillations on your plots? Did it come from oscillatory exponentials, or was
You mean
it
these?
different? Yes.
Yes, so these do come from the exponentials in your trend series. So the exponential of the instant on action over GS. If you go into the complex Toph plane, which I did here, that exponential is going to start oscillating.
And they are pure oscillation, or was it for just some numbers with the non-trivial imaginary parts?
Sorry, say again?
Were they purely imaginary, or?
No, they have non-trivial real and imaginary parts, yes. Yeah. Yes. Yes, but our spectral geometry methods still work even for that spectral curve. Yes, so one of the things that we're looking at is how to make sense of that infinite sum of infinitely many sigmas. Yes, that's an important problem that we're still addressing. Yeah, that's a good point. But we believe that things still work. Yes. Yeah. Yeah.
Discuss much, which I'm happy about. So yeah, I missed the point. If you said that it's some graph that it's crucial to include the contribution, otherwise you would never match, right?
Yeah.
So on the other hand, if I consider again some physical problem, I mean, I don't know, GS, real, the contour I start with real, or something which at the end of the day I know it's going to have some whatever physical meaning, then I don't really understand. First of all, I mean, we would like to understand what they correspond to physically.
That's fair.
Aside from oriental plates, which I don't think they play a role here, we don't have such structure, right? So we need to understand.
Sure. Sure.
But also, more very trivially, whenever you have an asymptotic expansion perturbation theory, the leftover pieces that you are missing should be small. We expect to look at. Not can be large, because if they are large means that your perturbative expansion is simply not the correct one. Just by definition. When the coupling is parametrically small, perturbation theory should be great, because it's asymptotic. It should be better and better. So there is no room for asymptotically enhanced contribution in a well-defined perturbation theory asymptotic expansion, just by definition. So from this point of view, I didn't really understood how you could get this exponentially enhanced contribution.
Right. So your initial question is if I stay on the real line, for example, of the Toph coupling plane? Yeah? Okay. So let me go back to that phase diagram that I showed you here for the cubic matrix model. I told you in my introduction. Yeah, okay, sure. The quartic matrix model phase diagram pretty much looks identical to this. That's a very fair point. Yeah, thank you for that. So I told you about like these double scaling limit points, right? Where things from the large n perspective diverge, and then you can do this double scaling limit to get to string theories. I didn't tell you where those points are in this diagram. They're the triple scaling points, so they're here and here, and this is the real line. So if you insist on keeping the Toph coupling strictly real, and positive real if you want, You can start here at weak coupling and then flow right up until here, and then you run into your singularity, and you need to somehow. So if you you can't directly go through this point from the large n point of view, so you will have to walk around it. But then and then go back to the real line, and then you can go to strong coupling just fine. But you cannot do this in any way without crossing that Stokes transition that switches on negative tension effects. I didn't add the Stokes lines in this graph, but the Stokes lines emanate from these points also in this direction and that direction in such a way that it's impossible to avoid.
The light ellipse is on the right, the small one. Then it should be deactivated. So this is my word. Then it should be around the origin, which they are deactivated. Then if they activate a strong coupling, fine. The strong coupling, 1 over G, cannot explode. Right?
Sure.
The wedge, the smooth wedge, which includes the origin, which is where parametric should apply, should be deactivated.
Yes.
Right? So they are activated somewhere, it's a strong coupling. Okay.
Yes, they activated that strong coupling. Here, you're safe. Here, the negative tension stuff is exactly 0 in order to match finite n, and it only happens as you go to a sufficiently strong coupling. Yes, it's a good point. Yeah.
Physics-wise, we have an understanding what they can correspond to.
Not a complete one, and that's a very fair point, but there's, so my advisor, Ricardo, did a side project on interpreting these matrix integrals that I showed you from the boundary conformal field theory point of view and constructing them in that sense, where essentially the bottom line is that these integrals over non-perturbative Lefschetz symbols become like the moduli space of some FZZT brane. Like there's a way to start from this language and exactly get these types of integrals out. This is the most physical picture that we have for this. We did not use that much in this project because as hard as these matrix integrals are from this point of view, they're even harder to construct correctly from the BCFT point of view, which is why we didn't go into it much, but that's a way to look at this. Yeah. And then negative tension effects can be interpreted as negative tension FZZT branes, which are basically FZZTs that are reversed in space-time. Yeah.
Why couldn't you, like here with the previous slide that you showed, go through this pinching point and just a singularity of the partition function?
Sorry? What was your question?
You said that
Picture?
if you start in this gray area
on
the real line and you start going to the right, you somehow have to go around this particular pinching point.
Yeah.
So all three colors meet.
Yeah.
And why can't you go through it? Because that's the singularity of the partition function.
Yeah, it's a singularity that appears from the large n point of view.
Just tell you that there is a phase position there, and so there isn't if you ever go through it, is because you need to somehow not go through this singular point, which is the same, not go directly through.
Yeah, so from the finite n point of view, things do make sense here, right? It's just this is a large n artifact, and we did some tests where we looked at okay, if I add a larger part of my trans series, can I, from the large n point of view, can I get closer to this point without things blowing up? And you can. So if you resum things cleanly, as I showed you, you can get as close as you want, given enough data. So this is an artificial thing.
Yeah, but in terms of your expansion, your asymptotic expansion, where you have these negative tension things, this should tell you that in some sense they should condense on the other side of this phase position. Or this phase position which are applied between them.
Sure.
So what you see is that you have this object in your system that you sort of discard as long as you're on one side of the phase transition. You have to take them into account on the other side of the phase transition, and somehow these analytic continuations tell you how you should regulate this transition.
Yes. You can look at things from a condensation point of view. That's a way to think about this diagonal framing resummation that I was talking about. Because basically, so you do this collecting exponential weights, right? And then you resum things. the variable that you get is mu, which is like a product of sigma 1, sigma 2. So you can think of this as like summing different like positive, negative tension pairs. So there is a way there to think about things as like a condensation process. Yeah.
What is the precise meaning of this diagram? Because for cubic potential, it seems that we have two coefficients. One coefficient is on the overall one, and another is coefficient in front of the linear part. We have lambda cubed plus some t times lambda divided by gs.
Mm-hmm.
So what is your potential in this problem?
I'm sorry, I don't think I've caught your question.
What is the meaning of this diagram?
Yes.
In a sense, there is one parameter in the potential itself.
Mm-hmm.
So where the parameter
Yeah, so we fixed everything except for t.
But is there a statement that this picture is the same for any value of the extra parameter in the potential?
For the particular case of the cubic, yes, because you can always scale that extra number away, because there's not enough terms. There's few enough terms. But what I mean by cubic is a cubic polynomial that has a quadratic and a cubic part, and the linear and the constant part we don't care about. And then you can always rescale your variables in a way that thing doesn't make sense, that thing disappears. Now, for more complicated potentials, yeah, there's going to be extra variables, and then this picture can move around a bit. Then things can deform, and there can be extra faces here that correspond to different amounts of cuts opening up. That's true.
No, we can't scale them in the cubic case because we have the overall coefficient that can encode all this scaling, and we have a relative coefficient between cubic and linear. Like there are different types of cubic potential. Either lambda cubed O0 or lambda cubed plus something with very distinct zeros. So what is your potential?
So my potential, as I said, is just basically lambda cubed plus something lambda squared. There's a linear term that you can add a linear term, sure, but you can always linearly shift your variable such that the linear part disappears, and then the constant term you don't care about.
But there is one parameter in this potential.
Yeah, and that you can rescale. You can set to 1 by rescaling your lambdas, rescaling your lambda variable. Maybe I can show you after, but this is in this case this is really fine. There's no other parameters here. Okay.
Other questions, comments? No. Okay, so let's thank Jasper.
Thank you.